In the last lecture, we had concluded the following. We concluded that there was a map between two classical differential equation problems. The first classical differential equation problem was solving for the motion, the long wavelength motion for of horizons in large D, where long wavelength was long wavelength on the scale of R0 divided by D. Okay? So any reasonable length scale, any D-independent length scale for your orbitals was okay, was considered as long wavelength for this purpose. So on one side we had, let's just call it reasonable. Okay. And the other side of the duality was to solve for the motion of a membrane. So membrane, remember, was a codimension 1 object. Okay? A codimension 1 object that lived in the flat space. By the end of this lecture, I'll tell you with many generalizations of the story, but we are working on the basic story. Okay? So the membrane is a codimension 1 object that lives in flat space. The degrees of freedom of this membrane are its shape and a velocity field. On the membrane. Okay? And we had some equations, membrane equations of motion that I'm not going to rewrite. One of the equations was del dot u is equal to 0. This was leading order equation. At leading order, there was another more complicated equation that involved del kappa by kappa and del square u. You know, that series of terms that I would rewrite for you. One important thing about this about the membrane problem was that there were as many equations as variables as we counted. And so at least plausibly the membrane equations of motion define a good initial value problem. Now, let's take 1 minute to be able to think of this. To think of this membrane, what you should think of is like a soap bubble in flat space. Okay? So there's this soap bubble that's floating around in flat space. The soap bubble is characterized by a shape, but the soap bubble is made up of some stuff. And that stuff can be moving. Now, of course, the soap bubble can move orthogonal to where it is. It could be here and then go here. That motion is captured by the shape as a function of time. However, in addition to this, the soap bubble can be moving in its world volume direction. You can imagine a soap bubble that's some shape, let's say an ellipsoid, and rotating. That's a different state from the soap bubble not rotating. Okay? So the degrees of freedom of our membrane are very much like that of the soap bubble in the sense that you have to keep track not only of the shape of the membrane, but of the velocity of the stuff that is making up the membrane. Okay? And that velocity is, by definition, in the in-plane directions. Remember that our u was in the membrane world. Okay? There is one difference, though, between the soap bubble and our membrane. And that is this. Inside a real soap bubble, in what we're looking at, there's air. You know, space exists outside and inside the soap bubble. And, okay, also it's not very important, there's air also inside. Inside our soap bubble, there is nothing. Our soap bubble, our membrane, is an end of the world membrane, as far as we're concerned. Okay? Our effective space-time ends there. There may or may not be something inside, we don't care. From the point of view of our description, there's nothing inside. Okay? Certainly there's no air inside. Nothing pushing back on the soap bubble like a real soap bubble. Okay? I emphasize this because people sometimes are confused. And the source of the confusion is this. As you learned when you're studying real soap bubbles, you know, the reason a soap bubble is stable is that there's surface tension which tries to push the soap bubble this, and then pressure from the air which tries to resist it. And that's the dynamics of equilibrium of a real soap bubble. We've got a very different kind of soap bubble because there's no air, there's nothing to push back. So in particular, our soap bubble has no surface tension. And this is reflected, or will be reflected in my stress tensor as I will write it down. You will see this as we, at leading order, our soap bubble lacks a surface tension. Because if it had a leading order surface tension, our membrane like this would just want to collapse, and then stationary bubble solutions of arbitrary size would not be solutions. But of course they are, because those describe backwards. Is this clear? Okay? Now, to understand our soap bubbles better, to understand our membrane better, to understand intuition for this dynamics, and to understand the nature of the equations of motion better, we're going to rewrite the equations of motion of the membrane in an interesting way, in a way that is reminiscent of the equation of fluid dynamics. Namely, what we're going to do is to rewrite the equations of motion of the membrane as a condition of the conservation of a stress tensor that lives on the membrane. Now, one could actually have done this just as an algebraic exercise. Just try to invent a stress tensor that lives on the membrane, such that its conservation would give us the equation of motion we've derived. But we're going to approach this from a logical point of view that will give us additional benefits. Okay? So, in order to get to this point, the question we're going to ask is the following. We're going to ask, well, suppose I've got my membrane, it's undergoing some motion according to its equation of motion. The question I'm going to ask is, as it undergoes its motion, what effect does it have on the space-time far away from the membrane? Now, if you remember the general logical structure of my lectures, one of the things I emphasize many times is that in our ansatz, the influence of the fact that you had a black hole at all dies off very fast as you move away from the black hole. So if you're far away, you hardly see the black hole. The effect of the black hole being there at all is exponentially small, indeed. And this is correct. So the effect of this black hole on the outside is going to be extremely small, exponentially small indeed. However, whatever it is, what I would like to do is to compute the leading contribution to the impact on the outside of my membrane. Okay? Maybe very small. It may be very small. Nonetheless, I should be able to capture the leading order contribution, however small it is, in the large data. Now, what do we expect this leading order contribution to be? Well, this membrane is, it's behaving very much like it's something sitting inside space-time. And whenever you've got a thing sitting inside space-time, it interacts with space-time just because it carries energy. And it should cause radiation. So as this membrane moves around, what it should be doing is radiating outside. And the question we're going to pose is, can we accurately capture the radiation of this membrane as it moves around? Can we understand from another point of view why this radiation is so small? And that answering that question will allow us also, as a bonus, to better understand the equation of motion of the membrane. Okay, so the question we're going to pose ourselves over the next 5 to 10 minutes, I'm going to go very fast because we have lots to say in this last lecture, is, can we understand the radiation from the membrane as it's moving around? Now to understand how the logic for this is very simple. You remember that what we've done is to compute these membrane solutions in a neighborhood of the membrane. Okay? We computed these solutions in 1 by d expansion in this coordinate r. You remember r was d into rho minus 1. D into rho minus 1. And our solutions were valid for arbitrarily large r. But you remember that all our solutions decayed like e to the power minus r. So where, in a regime where the solutions were valid, the solutions became very small, represented very small fluctuations around flat space. Okay? So we've done a computation with one approximation. The approximation being we stay near the membrane. We stay near the membrane. All the approximations we talked about last time, the logic last time. And we got valid results, at least at finite r. Actually, it turns out that the validity is a little larger. It actually turns out that what we've done is valid for rho minus 1, much less than 1. Not necessarily of order 1 by d. But it's unimportant for what I'm going to say, so I won't discuss it. Okay? So in one region, we've accurately solved the equations. Now we expect that this is going to lead to radiation. Now, to understand radiation at leading order, you only need to solve Einstein's equations in the linearized regime. Okay? But we've already seen that our solutions become very small deviations around flat space and therefore become linearized solutions to Einstein's equations within the validity of our procedure. Therefore, in order to understand radiation, all we have to do is to take our solutions, look at what they become at large r, and then match these solutions to linearized solutions of Einstein's equations, which will now be valid everywhere outside the membrane. Because when you've got small radiation near the membrane, it just gets smaller as you go further. Farther. Is that clear? Yes. Yes. So we solved our membrane equations, assuming we were in a neighborhood of the membrane of size of order 1 by d. Okay? So our rho minus 1 divided by d was equal to r. Okay? So we haven't solved the equation, we haven't solved Einstein's equations everywhere. In particular, we haven't solved the equations far away from the membrane. Okay? It didn't bother us very much because we knew that this is very close to flat space, far away from the membrane. But suppose we want the leading deviation from flat space, our work hasn't got it. Okay? However, it has got it when, for all values of r. So rho minus 1 divided by d is r, even if r is 1 millionth, we've accurately found the solution. Now something that you might remember is that all our solutions represented deviation from flat space, deviated from flat space like e to the power minus 5. If you look at our zeroth order ansatz, it approached flat space like e to the power minus 5. Do you remember this? Should I remind you? It's simply 1 over rho to the power d. Let me tell you why. Okay. For instance, in our zeroth order ansatz, we have this factor 1 over rho to the power d minus 3. Let's call it 1 over rho to the power d because d and d minus 3 are the same in these large. Okay. Let's write this as 1 over, so we'll expand this around rho equals 1. So 1 plus rho minus 1. And then I'll write this as divided by d to the power d. I mean, times d. And then this is to the power d. Now this whole thing was r. Okay, so that's 1 over 1 plus r divided by d to the power d, which in the large D limit is e to the power minus 1. So you remember that our zeroth order ansatz approached flat space like e to the power minus 1. The same thing was true for all our connections. That was one of the boundary conditions being required. Okay? So, where we have accurately solved the equations, okay, in the regime r is much greater than 1, our solutions deviate from flat space only in a small way. Therefore, the solutions must, at large r, reduce to linearized solutions of Einstein's equation around flat space. Because the metric is a small deviation around flat space. We've solved it everywhere in non-linear manner. But at large r, it must be the same thing as solving linearized Einstein equations. Okay? So all we have to do is is to identify what linearized solution of Einstein's equations this is, and continue that linearized solution all the way to infinity. So I say it another way. There are two different approximation schemes that have an overlap of domain of validity. The first approximation scheme was our membrane solving. This was a non-linear procedure. Its limit was that it worked only near the membrane. But it works for all values of R. So in particular it works for R order 1 or R large. The second is linearized solutions to Einstein's equations, which work only when the deviations from flat space are small. Okay? There's an overlap in the validity of these two approximations when R is large. Because we're both near enough to the membrane for our first approximation to be valid, as well as the deviation from flat space is small enough for linearized. Is this clear?
It's a match asymptotic expansion.
Exactly. Okay. So, in order to find out what our radiation is going to be in infinity, all we have to do is match these two different approximations. Now, you see, what we need to do is to read off the particular linearized solution to Einstein's equations and then continue it. But there are two separate questions that we can ask ourselves. How do we read off the particular linearized solution to Einstein's equations? That's totally trivial, right? You just take our solutions and go to that. A. B. How do you continue this to infinity in a practical manner? The second step can be done in a clever way, which I'm now going to explain to you. I will explain it to you in the case of scalar field, okay? Just because the algebra is easier, but then give you the answer in the case of the dimension. Okay? So the problem that we want to understand is this. We've got some surface, and in the neighborhood of this surface, we have a linearized solution to Einstein's equation. And we want to continue this linearized solution to arbitrarily large R. Question, how do we do it? Okay? I'm going to answer the same question for the equation del squared phi is equal to 0. And then though there are further bells and whistles in the case of the Einstein equation, the basic idea is the same. So I won't be able to show you the details of the Einstein, it's too complicated. But I can more or less show you the details. It's simple. Okay? It's the same general principle. Okay. So, what I'm going to do in order to address this question is the following. Given, suppose I've got some particular surface. This surface, as always, is the surface rho is equal to 1, where my equation rho satisfies this lovely equation, del squared rho to the power minus 3 is equal to 0, the equation that we demanded in the construction of our solution. So, what I'm going to try to do is the following. I am going to do the following. I am going to construct the most general solution of del squared phi is equal to 0. Okay? I'm going to construct the most general solution of del squared phi is equal to 0 that on this membrane at rho is equal to 1 becomes phi is equal to phi naught of surface, of membrane. So I've got a boundary value kind of problem. I know that my phi is some phi naught on this boundary. Let's suppose I know that my phi is some phi naught on this boundary. I'm now going to try to construct the most general solution of the equation del squared phi is equal to 0. Okay, that agrees with that, it reduces to phi is equal to phi naught on this boundary, and then decays, becomes small at infinity. I'm actually also going to construct, though it doesn't physically exist, a second auxiliary solution. I will construct a second auxiliary solution to the equation del squared phi is equal to 0, and this solution will be another solution which agrees with phi is equal to phi naught on the surface, but is regular everywhere inside. Okay? Once I have these two solutions, I'll be able to do something clever. So before we get to the clever thing, let me first go through the slightly grungy work of constructing the solutions. Okay? Is the whole clear?
The second solution is non-physical physics and the solution to an observer and asymptotic infinity beyond the singularity.
Beyond the singular? No, the second. You see, the second, because actually in our problem, there's no linearized Einstein equation in here. Einstein's equation becomes horribly nonlinear. So the second solution is just something in our head. It's just some device that will be used for purposes. Okay. The trick that allowed me to construct these solutions is very similar to the trick that allowed me to construct rho in a power series expansion away from my rho equals 1 surface. And it crucially uses logic. Okay? So you can do it in many ways, but the easiest way to start is with a guess. Look, suppose we wanted the solution. Suppose we wanted the solution, the solution to the equation phi is equal to phi naught, and obeying del squared phi is equal to 0 everywhere outside. And suppose that we had the following particular case, that phi naught was a constant, let's say 1 on the surface. Then what's our solution? Well, suppose phi naught was 1, then we know that phi is just 1 over rho to the power d minus 3 outside, and phi is equal to 1 inside. Obviously, 1 is a great solution to the equation, and it obeys our boundary condition of regularity inside. 1 is not the right solution outside because it doesn't decay infinity. But we know the solution that does decay infinity is 1 over rho to the power d minus 3. That was our definition of rho. That's how we constructed it. Okay? Now, let's put this aside for a moment and look at the outside solution. The outside solution is decaying very fast in the d direction. We will assume that our phi naught is a slowly varying function, varies on length scale 1. Okay? So locally, phi naught is near to being a constant on the length scale of variation of this rho to the power d minus 3. And therefore, it's not unreasonable to guess that locally the solution will look like phi is equal to phi naught of x divided by rho to the power d minus 3. This is our guess for the first leading order solution, and then we'll have to correct it. Okay, this guess turns out to be correct, but even in order to say what this guess, even as a statement of what the guess is a bit ambiguous. Because x is a coordinate just on the surface. And what I'm trying to construct here is a function in space-time. So what does it mean that phi is equal to phi naught of x divided by rho to the power d minus 3 if at some point that's not on the surface? This is not a well-defined function. It's not. I've not yet told you what the guess is. Of course, as in perturbation theory, it doesn't matter how, it doesn't really matter how you extend this phi naught off the surface. So we'll choose a convenient frame choice. We will choose phi naught, let's call this phi naught tilde of x, such that phi naught tilde of x is equal to phi naught of x on surface and obeys the equation n dot del phi naught is equal to 0. So that if you want to construct it away from the surface, then d rho dot del of phi naught is 0. So that's constant along lines, along these normal vectors that are normal to the surface of constant lines. So that's how we extend it off the surface. Yeah, that's just a convenient way. Okay, so this is my guess for what the solution is. Now it turns out, when you think about it, that the correct solution is this plus a power series expansion of rho minus 1 to the power n times some, let's call it beta n of x, all divided by rho to the power d minus 3. Turns out this ansatz works. And you can correct it order by order in distance away from your membrane. Rho minus 1 is a measure of how far you are away from the membrane. And in the large D limit, you can effectively solve for each of these beta n of x's in terms of phi naught of x in a 1 over n, or in a 1 over d expansion. I'm going to show you the lowest order of this expansion and then just indicate how it works. Okay? So the lowest order, we'll just keep phi naught of x divided by rho to the power d minus 3 plus rho minus 1 times beta 1 of x to the power rho to the power d minus 3. Now, Once again, my beta 1s are going to be functions just on the boundary, functions defined by data just on the membrane. I will assume that all my beta n's obey this kind of constraint. N dot del of beta n is equal to 0. So though beta n's are functions on spacetime, the data of these functions is entirely in functions on the membrane. Okay, so all I need to do is to find beta n on the membrane, and then in principle I know that. Okay, so let me now try to find it. What I want to do is to apply the equation del squared of this is equal to 0. Now let's see what happens when you take del squared of phi naught right by rho to the power d minus 3. Firstly, what should you expect at leading order del squared on a function like this to be? Well, it's the same argument again and again. Del squared is a two-derivative operator. Things vary on length scale 1 by d, so you should expect del squared to be order d squared. You know you've got an approximate solution to your problem if you're doing better than d squared. Okay? So let's see if we're doing better than d squared. Let's see. Del squared acting on this has three terms. The first is del squared of phi naught divided by d rho to the power d minus 3. Then there is a del phi naught dot del rho. So that's 0 because of this. And then there is a del square of 1 over rho to the power d minus 3. So that's 0 because of the definition of rho. Rho was a function that obeyed del square of 1 over rho to the power d minus 3 is equal to 0. Okay? So when we have del square of this object here, we only get this one. Is this clear? Now let's add del squared. Notice that this is order d. You might remember that according to our counting, del squared of an order 1 function was order d. D is better than d squared, so we're doing well. Okay? That more or less guarantees that you'll be able to correct it. Now I'll show you how you can correct it first. Okay? So we like del squared of this object here. Now if we didn't have this rho minus 1, it would be the same thing. So one term will of course be rho minus 1 times del squared of beta 1 x. Okay? However, now there are additional terms because of this rho minus 1. What are the additional terms? One additional term is when del acts on this rho, and one del acts. Okay? So that will give us minus 2 into d minus 3. And then we get del rho del. Del rho del. Times beta 1. That's one term. And finally, there's one more term. Okay? Plus, there's a term where del square acts on this. Del square rho times beta divided by rho to the power d minus 3. Now, if you remember the equation that del square of 1 over rho to the power d minus 3 was 0, gave you an equation relating, del square rho with del rho dot del rho. If you open that equation out, that's what you got. We got this out in the last lecture. Okay. You can use that equation to trade this del square rho for a del rho dot del rho. And when you do that, turns out, the details are not very important, but it turns out that this becomes minus d minus 4. So from the condition that del squared 1 by rho to the power d minus 3 is equal to 0, that term is the same as this term with the additional fact. Okay, now we've got three terms. And at first sight, this sounds like a complicated partial differential equation for beta. Because we've got del squared of beta, and we've got beta acting on this stuff. Okay? But suppose we're interested at rho equals 1, in the place rho equals 1. Then the del square of beta is just not there. More generally, if we're interested in distances rho away from 1 of order 1 by d, this quantity is order d. This quantity is order d because of the del square times order 1 by d because of the rho minus 1. Right? Because rho minus 1 is of order 1 by d where we're interested. Okay? But anyway, for this purpose of this this calculation, let's just do it at rho equals 1. So this term goes away. That leaves this term. Now what we've got is not some complicated partial differential equation in beta. We've got an ordinary algebraic equation in beta. You might remember that we knew what del rho was. It was something particular in terms of the extrinsic curvature of the membrane. You remember when we solved for rho away from the membrane, we had this equation. The point of that solving was to find del rho, the norm of that, of the normal vector. So this is something known. I won't write it down for you. But because this is known, we know what beta 1 is. So beta 1 is something known. It's proportional to del square phi naught. And then there are some kappas along. Turns out, up to the factors I won't get straight, beta 1 is like del square phi naught times kappa. Trace of extrinsic curvature. So we found that phi is equal to phi naught plus rho minus 1 del squared phi naught. Remember, del squared is just del squared on the membrane. Okay? This del squared is just del squared on the membrane. Del squared phi naught divided by rho to the whole divided by rho to the power d minus 3. And actually, you can continue this to arbitrarily high order. You can continue to arbitrary order in the Taylor series expansion to rho minus 1. And also compute each of these coefficients accurately in a 1 over d expansion. We don't have time to go through the structure of this expansion, in a way not very important. But you can do this. Now, this I did outside the membrane for solution number 1, the solution that's valid outside. But I can do the same thing for inside the membrane. Okay? The same procedure carries through, similar expansion, same procedure, and you get a similar result. Phi is equal to phi naught plus something times rho minus 1. Again, there's a del square phi naught there. It doesn't matter, the details don't matter, just goes on. The important thing is we've managed to solve the equation both a little bit outside and a little bit inside, just in terms of the data of the solution on phi naught. Now, why is this important? This is important for the following reason. You see, we've solved the following problem. We've solved the problem of finding a solution to del square phi is equal to 0 that is a solution everywhere outside the membrane and everywhere inside the membrane, but not on the membrane. Because on the membrane we've got a discontinuity in derivative. Phi naught is continuous, but its derivative is not. Okay? But if that's the case, then every such solution is in fact the solution to the equation del square phi is equal to j, where j is a count that lies distributionally delta function localized on the membrane. Okay? And what is the value of that count? Well, suppose you take the equation del squared phi is equal to j, where j has a delta function, delta of rho minus 1. And you do the pillbox kind of trick. You take this equation and integrate it a little bit outside and a little bit inside on a pillbox surrounding the membrane. You will convince yourself that j is proportional to the discontinuity of del rho phi out minus in. There are additional factors that I'm not writing down because we don't have the time to do this. You understand? The discontinuity of the normal derivative, this is the kind of thing that you do when you study Jackson. The discontinuity of the normal derivative of phi gives you j. So, what we have done is the following. We've traded the knowledge of the solution on the membrane for a current on the membrane. And the solution outside is a solution to the equation del square phi is equal to count. Now we're in business. Because if we know the current on a surface and we want to find the solution far away, we know exactly how to do it. We use all our hard-won knowledge of electromagnetism, that kind of stuff. We know that the solution is phi of x is equal to integral g of x minus x prime j of x prime, where j is the current and g is the principal. This current is delta function localized on the membrane. This gives us the formula for the answer. This sounds great. This sounds great. Except for one confusion. But before we come to that confusion, I'm just going to say the following. That exactly this procedure can be repeated for the metric. There are a few more complications for the metric because you have to ensure that the current that couples to the metric is not just any old current but a conserved current. This of course comes out directly from the procedure, but there's a beautiful structure to see how it comes out. So there's more to say with the metric. But basically it's the same idea. And when you go through it, you have the same result for the metric. So if you knew what your solution was on a surface, or in the neighborhood of the surface, as we do in our membrane problem, you can trade that solution, in the case of our membrane problem, for a stress tensor that lives on the membrane. Is this clear? Okay? This logic that I've outlined only very roughly because we are running out of time, allows us to trade our knowledge of the solution in the neighborhood of the membrane for a stress tensor that lives on the membrane. Yes?
Didn't you need to have some sort of notion of the solution inside in order to take the jump?
Yes, you did. But we produce that solution inside just as a fictional device. So you see, what we do is the following. We take our solution, which was a nonlinear solution of Einstein's equations. Then we go to large R and identify the linearized solution of Einstein's equation. And then we solve the following auxiliary problem. Now we throw away nonlinear Einstein's equation. We just concentrate on the linearized Einstein equations. Okay? And ask, can we find a linearized solution of Einstein's equations that's exactly a linearized solution of Einstein's equations everywhere outside and everywhere inside?
Why is that a good requirement?
That's just a mathematical requirement. All we want to do is to take this linearized solution outside and continue to infinity. So as an auxiliary mathematical device, we're going to solve this problem, which allows us to do that. You see, because the problem is a well-posed problem of mathematical physics. Given a linearized solution of Einstein's equations, you have to continue it to infinity. If you do it any way you can, you've got the answer. So we're going to solve it by inventing some bells and whistles that don't exist in the physical problem, but that are useful.
So you change up the solution inside to just leave it less than so, but no.
No, the solution inside is totally uniquely determined. You see, just like the outside solution, phi naught determined both the outside solution and the inside. So there's no data in the inside solution.
Why do you require it to be regular inside?
Because if it was not regular inside, then our solution outside would, if it was not regular inside, then there would be effectively sources inside as well. So our solution inside would not be the integral of a Green function over a current that lay entirely on the membrane. Okay, now you can do that, but there are many solutions to this problem, but we want one in which the sources lie entirely on the membrane. That is unique. Let me say it again. Suppose you have some source here and some source here. It's true that you might be able to get the same solution outside by distributing the sources differently. But we're not interested in that. We want the solution whose sources lie entirely on the membrane. It's just going to be convenient. Okay, fine. It's because the stress tensor we produce, okay, from this point of view, will be the stress tensor that lives on the membrane and that will produce the right radiation field at infinity. You might have been able to do something else.
So I'd be worried that in practice there's a singularity there, and maybe I have to include that in order to talk about the radiation that's coming out or something.
But because saying that you'd be worried that there is no regular solution. No, but there are regular solutions. We found it. You see, okay. We have a proof that the solution is regular all the way. Certainly in examples I could solve the problem and show you there is a regular solution. Okay, I suppose you're worried that there does not exist a regular solution inside. In perturbation theory we find it. Now if some non-perturbative problem. Okay, yes. Yes.
Here, because you said we have to take the linear solution to the infinity.
Yes.
But actually, as we mentioned, we have identified infinity to the outer shell of the.
Yeah. So it's true that the solution from the outer shell up to infinity is very small. It's a very small deviation from that space. But we're interested in determining that very small solution. It's true that the deviation is very small, but we want to determine it. Hang on for a minute, it'll become clearer in a minute. Amos, how much time do I really have?
Try to finish by 2.
By 2, which is 20 minutes? No, that's fine. Yeah. Okay. Okay. Assuming Amos is worried, assuming the regular, there's no obstruction finding the solutions, which I repeat, we find in perturbation theory. Okay? But assuming that there's no issue with finding the solutions, we have the stress tensor on the membrane. Now, of course, yeah. Now, before we get back to that stress tensor, which is the real goal of this exercise, I want to address another issue that might occur to some of you. And this other issue that might occur to some of you is the following. It is that this solution doesn't look like it's unique. This solution doesn't look like it's unique because you see there is no such thing as a unique Green's function. Green's functions come in many shapes and flavors depending on the boundary conditions that are infinite. For instance, for the equation del square phi is equal to 0, all of us are familiar with 3 famous Green's functions. There's the retarded Green's function, there's the advanced Green's function, there's final Green's function. Which Green's function should we use? Well, of course, physics tells us which Green's function we should use. Okay? Physics tells us that the Green's function that we should use is the Green's function that corresponds to outgoing radiation energy. Because if we've got a black hole that starts doing something, it's going to let out radiation. We want to solve the following problem. We want to solve the problem of a black hole moving without something coming, not being pumped by radiation coming from inside. Only radiation going out. It's the same boundary conditions as the quasi-normal problem. No ingoing radiation, which means the retarded wave function. So from the point of view of physics, this is G retarded. Okay? However, in everything I described to you, nowhere did I use that boundary condition. Nowhere did I use the boundary condition that our solution has to be outgoing and infinity. In this algebraic stuff that I described to find the solution of rho, the power series expansion rho minus 1, nowhere I use that boundary condition. So had I used another boundary condition, had it been incoming for some particular reason, I would have got the same solution. So now it looks like we've got a contradiction. Because the same logic tells me that this phi, at least at small distances, the phi's that I produced here, should also be produced by convoluting, let's say, the advanced Green's function over this source. Okay? So let me say it again. I've done 2 things. First, I've got phi on the membrane, and I produced phi outside in a power series expansion. Just algebraically. Now I've got another claim. I've got another claim for what phi is. Phi is given by this, where I've identified J. These 2 things should be the same. However, it looks like 2 different formulas. Phi with G retarded and phi with G advanced should both give the same answer. Because the algebraic procedure made no reference to the boundary condition at infinity is entirely local. How can this be true? This can only be true if at large d, the retarded and advanced Green's functions don't differ very much at distances, at small distances. That's the only way this could possibly be true. Indeed, that's the case, and I'm now very quickly going to show you. So we can take a 5-minute diversion to understand Green's functions at large. So, what's the Green's function? The Green's function is the solution to the equation del square g is equal to minus delta. Delta is the delta function. Okay? This is del square in space time, but for various reasons it's convenient to understand this Green's function as space and time split, to break the rate. Okay? So I'm going to write g is equal to g omega of r. R is just a radial coordinate, polar coordinates in space, times e to the power I omega t. And I'm going to rewrite this equation in terms of g omega of t. Okay? So what's the equation? The equation is 1 by r to the power d minus 2 del r to the power d minus 2 del r g omega of r plus omega squared g omega of r is equal to 0. Is this clear? I've rewritten del square as del square space plus del square time. Del square time is just plus omega squared. Minus d by dt squared, and then there's an extra minus sign because of the i's. And del square space, well, we've got a radially symmetric thing, so I've just used the formula for del square polar coordinates. Is this clear? Excellent. Is equal to, of course, delta. In fact, it's delta of r at every omega. The same delta, because you Fourier transform this delta in time, it's just one time. It's the same, it's no omega again. Okay, now what we're going to do is to solve this equation, first staying away from r equals 0. Okay? So we're going to solve this equation first staying away from r equals 0, and then we'll understand how to solve it even at r equals 0. Okay, so to solve it at r equals 0, away from r equals 0, I just replace this by 0. The delta function becomes 0. Now, what I've got is an equation that's not too different from a Schrodinger equation. Okay? Of course, this equation is trivial to solve. It's a Bessel function. But the important thing is not the solution, it's the properties of the solution, which are easier to see in pictures than to remember properties of Bessel functions. So I'll draw the pictures. Okay? This is not too far from a Schrodinger equation, except that in addition to two derivative terms, you also have one derivative. Because this del r can put this out. But of course, whenever you've got such a situation, you can redefine your function to get rid of that two derivative term. What's the redefinition we have to do here? Here, the redefinition we have to do is that g omega of r is equal to, let's call it some, zeta of r divided by r to the power d minus 2 by 2. Then the first derivative term hitting this from either here or here will produce a minus d by 2, which will cancel. This is easy to check. Okay? And the equation for zeta will become the following. It becomes d2 by dr squared zeta. And then, let me get the number right, minus d minus 2, which is d minus 4 by d minus 2 by 2 over d minus 4 by 2 zeta of r divided by r squared plus omega squared zeta of r is equal to 0. One mental value to go from here. Plug this into this, we get this. Okay? Now I want to write it like a Schrodinger equation. So first thing I do is I want to write it as minus del r squared plus d minus 2 by 2 in a d minus 4 by 2 so del r squared zeta plus zeta by r squared is equal to omega squared zeta. And now this is exactly the Schrodinger equation for a particle of mass, what is it? 2. Okay? Moving in a potential here is V of r and with energy omega squared. Okay? That's nice. Once we've got a Schrodinger equation, we can draw a picture. Okay. Once we've got a Schrodinger equation, we can draw a picture. The picture that's useful to draw is to draw V of r as a function of r. And if you look at this V of r, it's some huge positive thing called as d squared. that decay is like 1 over r squared. And then somewhere we've got an omega squared. This is omega squared. At some point, the potential goes below omega squared. Let me draw this a little less. Okay, forgive the drawing. This is the kind of thing if I was in a TIFR entrance interview, they saw the curve crossing it. You're not getting it. Okay. Okay. So forgive the drawing. Okay. So where does this omega square and the V of r cross? It's easy to check. So some value, but roughly it's at r is equal to d by 2 omega plus 1 by d direct. Easy to work out exactly. Roughly d by 2. So now we've got a Schrodinger problem where the potential is huge and above the energy axis for r being any reasonable value, less than d by 2 omega. But then the potential eventually goes below the energy axis for r greater than d by 2 omega. So, what are the two solutions here? What are the solutions to the Schrodinger problem? As I said, it's easy to work out the exact solution in terms of Bessel functions, but it's actually more instructive just to work it out approximately. So, firstly, in this large R regime, we can forget about the potential. So the solutions are phi is equal to a e to the power I omega r plus b e to the power minus I omega, obviously. What about the small r regime? In the small r regime, we can forget about omega because this guy way overwhelms this thing. And you find the solutions are phi is equal, well, it's homogeneous equations of powers, so then you have to work out the powers, and you find that the solutions are phi is equal to r alpha r to the power b minus 2 by 2 plus beta r to the power of by r to the power b minus 4 by 2. Okay? So inside we've got this solution. Outside we've got this solution. Okay? And we find the full solution by matching across here using, for instance, WKB matching formula. Okay. Now, suppose I was interested, I've written down the solution for phi, but what about the solution for g? For g, we have to divide everything by r to the power d minus 2 by 2. When we do that, this guy multiplies a constant. So g, this expansion is g is equal to alpha plus beta divided by r to the power d minus 3. You can check. Now, why is this important? This is important because remember we've solved the equation only away from the delta function. But we also need the solution of the delta function. But the solution of the delta function, you see, this equation, this r dependence, precisely obeys del squared of 1 over r to the power b minus 3 is a delta function. Okay? So, you get the solution including the delta function with the right normalization if you choose this to be 1. So there's no ambiguity in the normalization of this guy. These guys are all unfixed, but this guy is totally determined by the equation. Now, suppose I'm interested in the return Green's function. Okay, then I have to set b equals 0. I don't want the ingoing part. I have only a. Okay, I have to set b equals 0, and what I do is I take the solution here. I take it here, I use WKB matching formula to produce some linear combination of this and this solution, and then I adjust the normalization of the original solution so as to get this one right. Okay, that's how I get the whole thing working. However, now, how does WKB matching work? If you want to produce something nice like an outgoing solution, WKB matching works by having these two solutions, which were, I call it alpha here. These two solutions are approximately equal at the matching point. But note that this quantity here at the matching point is very small. It's 1 over d by 2 omega to the power d. So it must mean that this alpha is very small, so that at the matching point they become approximately equal. So this is approximately 1 over d by 2 omega to the power d. There are some numbers I'm not getting, right? But approximately this is this. Suppose I was matching now not to the retarded solution but the advanced solution. This number will change, but the order of magnitude will not. So for all reasonable range functions, this will be 1 over d to the power d plus 1 over r to the power d minus 3. And now you see that if I take this range function, the different range functions differ only in this number and distances of order 1. But you see that if I take this range function and I plug in r as some number of order 1, this is overwhelmingly greater than this, up to exponential accuracy in d. In fact, up to corrections of order d to the power d. So the retarded Green's function and the advanced Green's function agree with each other up to an accuracy of 1 over d to the power d. And that's why that made sense. That's why it was correct that you can use either the retarded Green's function or the advanced Green's function, and in a power series expansion in 1 over d just get the same answer. Of course, once you go very far away, it's very different answers. Physics tells us it's the right one. But you see, it's a key property of this whole thing. There are many things that come together to make largely make sense. One of which is that Green's functions up to distances of order d are universal. In fact, it's the same as the Euclidean Green's function, if you think through what I told you, up to a distance of order d. So all these Green's functions become Euclidean and universal up to distance of order d, and then start different. So that separation of scales makes all this work. Okay, great. So now that we've got rid of this, and I've got 5 minutes to go, let me see. So what you get is a stress tensor. Okay? Now, if everything's working out right, the stress tensor has to be conserved. Because it makes no sense to have a source for gravity with a stress tensor that's not conserved. Because if you did have a source for gravity with a stress tensor that was not conserved, you would get different answers in different gauges. The gauge invariance of your radiation is guaranteed by the conservation of the stress tensor. You just have this nonsensical formula, the stress tensor is not conserved. It's an intrinsic part of our procedure, of the abstract procedure. You take a linearized solution and produce a stress tensor. We show an abstract proof that you always get a conserved stress tensor. But of course, these abstract proofs, you should always check with explicit formulae. So we get a final stress tensor, and then once we get that stress tensor, okay, you can independently just check conservation by taking del mu t mu nu of that object algebraically. Okay? And check, is it 0 or not? And the answer is that at leading order, u m dot del n t m n turns out to be del dot u. And the other guy, projector p m n, del n of t n, p a n is proportional to the membrane equation. The membrane equation that I wrote down in the last lecture. Okay? I'm not writing it out. Okay, just a second. The stuff which was del m kappa by kappa plus all that. Okay, so it's really very nice. What we determine is a stress tensor on the membrane that sources radiation when the membrane moves around. For consistency, that stress tensor better be conserved, and it is. But if you just take that stress tensor as an algebraic expression and demand conservation, that is a cool way of rewriting the membrane conservation equations. The membrane equations. The membrane equations are no more and no less than the conservation of the membrane stress tensor with a particular stress tensor. Stress tensor that comes out of Einstein's equations. This may begin to sound very much like a fluid gravity map. Equations of hydrodynamics were conservation of the stress tensor with a particular stress tensor. Okay? And the form of that stress tensor, the function of velocities and shape, in that case temperatures, in our case shapes, comes out of the fluid gravity map. Okay. Now, last 2-3 minutes, let me I had misplanned these lectures. I should have had a little more time for some of this stuff. But let me very quickly tell you various things. I want to give you the form of the stress tensor. Okay? I'm only going to quote the leading order form, the form of the stress tensor that is correct in leading order, in the sense that it contributes to the leading order equations of motion. It actually takes a very simple and very elegant form. Okay. So, it turns out after some work that you can write the stress tensor as Tmn is equal to Tmn fluid plus Tmn total derivative. Let's first deal with Tmn total derivative. Okay, Tmn total derivative is equal to, let me get the number straight. 8 pi Tmn total derivative is equal to Kmn minus K Gmn divided by 2. On the other hand, Tmn fluid is equal to kappa by 2 Gmn minus sigma m. Let me tell you what all these things are. Okay? All these things go as follows. You see, Kmn is the extrinsic curvature of the membrane. Kappa is the trace of the extrinsic curvature. Now, Kmn minus Kgmn is a very particular combination of extrinsic curvatures. It's the combination that appears in the Brown-York stress tensor. Now, great thing about the Brown-York stress tensor is that it's the conservation of the Brown-York stress tensor is a statement of Einstein's constraint equations on slices. So if you compute, you take any solution to Einstein's equations, you slice it along any slicing, and you compute this form, sometimes this Kmn minus Kgmn on the slices, you will always get that will always be conserved automatically as an identity. Okay? But you know what are we doing in our membrane? We're taking our flat space, which is a beautiful solution to Einstein's equations, and slicing it along membrane volumes. Okay, this is the row slicing. So what we've got is this Kmn of rho equals 1. So in particular, in this slicing, this thing is conserved as an identity. Conservation of this thing is just automatic, it can be no information. Okay? So though this is there and sources radiation, it plays no role in generating the equations of motion. Is this clear? On the other hand, the equations of motion all come from taking the conservation of this stress tensor. And this, as you see, is extremely simple and beautiful. It is just the sum of two terms. One term is proportional to the metric of the oil volume and would have been a surface tension, except for the fact that the coefficient behind Gmn is not a constant, but is the extrinsic curvature, the trace of the extrinsic curvature. That's very important, of course, because as I said, if you have the surface tension, the soap bubble would just want to whoosh. That's not what one wants to happen. The second term is sigma mn. It is the same thing that we saw in fluid gravity map. It's the shear tensor, del m un plus del n um by 2. The coefficient of this term in any theory of hydrodynamics is called the shear viscosity. Okay, now if you take this stress tensor and you compute this object. I told you that at leading order you get del dot u. Okay? But at leading and first subleading order you get del dot u. But at second subleading order, we carried out this expansion to next order. Okay? You get a correction to del dot u. You get del dot u plus okay, I would write it plus 8 pi. Okay. This equation becomes del dot u minus sigma mn by 8. There may be a pi is equal to 0. Probably just this. This is the right equation that comes about working on the fluid gravity map. Indeed, if you take this stress tensor as I've listed it, and you compute this thing, the the divergence of the stress tensor dotted with u, you will find that exactly this equation comes out. Okay? So del dot u is not exactly 0, it's something. What is the interpretation of this? Our solutions have regular event horizons. And just like in the fluid gravity map, we can pull back the area form on the event horizon to the membrane and use it to construct an entropy current. That entropy current, to the order that I've been working, turns out to be simply um divided by 4. And as I tried to say in my colloquium, it's a general principle of these kind of equations of motion that they should locally obey the second law of thermodynamics. The second law of thermodynamics locally is the equation that del m gel m should be greater than or equal to 0. But now we know this is just del dot u up to some factor of 4, which we've calculated. Del dot u is sigma m and sigma m by 8. In fact, the form of the production of entropy is exactly like in hydrodynamics. Shear squared divided by viscosity. From this you can identify the viscosity and identify the entropy density, and you can check, surprise, surprise, that the ratio is 1 by 4 pi. It always is in these gravity calculations. Okay? Okay, I'm almost done, Okay. So this is a much more elegant way of understanding the equations of motion. Our equations of motion just have a fluid stress tensor. Look how simple this is. I mean, it couldn't be simpler and still be calculated. Okay? Take divergence of it gives you the Mendeley equations. By the way, if you correct the scale, this scale is trace of the extrinsic curvature, but if you add appropriate 1 by d corrections to it, this system of equations, this up to some fine print that I'm not advertising, this system of equations, and the statement is true without fine print, this system of equations is consistent, complete, and arbitrary d. It's a set of equations that you can study at d equals 4. It only captures black hole dynamics, that's largely. But it's a well-defined set of equations at every d. And has many nice properties at every d. It's a beautiful set of equations. What they're good for. Now, one last thing about these equations. I should have said many things, but okay, let me quickly say one last thing. First, about these equations, can you find solutions? Okay. Something that you can see immediately from here is, you see in hydrodynamics, there are special solutions that are stationary solutions. Stationary solutions are essentially rigid rotations. They have the property that their shear tensor vanishes. So if we study stationary solutions, okay, the stress tensor becomes even simpler. You just drop the sigma m. So it becomes really simple. Now, we have this intuition that a stationary solution should be a rigid rotation. So we just put that in. Let's check whether rigid rotations are solutions. So we put in a configuration of velocities that's a rigid rotation. So we take our spacetime, split it up into 2 planes, and set the velocity to be rotations in each of the 2 planes on some shape that we don't yet know. Okay? Now, if you plunge our ansatz into the stress tensor and demand conservation, you get the equation, you get the following. Del m of kappa divided by gamma is equal to 0. Where gamma is the gamma factor of the velocity. You know, you've got some velocity, which is some rigid rotation. You find the special relativistic gamma factor, u0 of that rotation, and you get this beautiful equation. In particular, for static solutions, gamma is just 1, and then the equation becomes del m of kappa is equal to 0. So you want to find solutions where the mean extrinsic curvature is constant. This is a famous problem of mathematics. 19th century people have solved. It comes out so fast.
Yes, there is log kappa.
Log kappa. Log, sorry?
There is log kappa.
But it's true.
Okay.
But if del m log kappa by gamma is equal to 0, so it's, yeah. So it's easier to say this way because this is constant. Okay? Now we've got a generalization of this beautiful problem of 19th century soap bubble physics to rotating problems. And this is the problem that you could try to solve to find myriads of stationary black hole solutions. Now that you've got these stationary black hole solutions, you can do more. Let's try to do dynamics. So let's take the simplest of these solutions, which is just a sphere. Sphere of arbitrary size, and linearize the membrane equation around it. It's a beautiful problem which you can solve very easily. And anyway, what you get is a spectrum of fluctuations. And the spectrum of fluctuations that you get agrees, actually up to second subleading order in the 1/d expansion that we've checked, with how we started these lectures. You may remember that we started these lectures with the assertion that Minwalla, Suzuki and Talabe had solved the quasi-normal mode problem around these black holes and found two sets of quasi-normal modes, light and heavy. We started out by trying to find a nonlinear theory of the light modes. We found these membrane equations. Is what we found the nonlinear theory of the light modes? Well, if it is, then we take this nonlinear theory, we linearize it around the spherical solution. We should recover the spectrum of Minwalla, Suzuki and Talabe. Indeed we do. Order by order, and, a leading order, first subleading order, second subleading order. So, well, there's a good check that we got the right equations. Last thing I'm going to say is that we've also generalized this to include Maxwell fields. We're solving not just Einstein equations, but Einstein-Maxwell equations with large D. There's a generalization, in addition to stress tensor, there's a charge current, both are conserved. Very nice equations, you can find the condition for stationary black hole solutions with charge. It's a nice story. Okay, that's it, my time's up. Let's stop. Let's stop.